Hello everyone, this is Kalpana here. In this video, we are going to solve a differential equation from higher order linear differential equation. So let's get going. Problem. Solve d square plus 1 into y equals to e power minus x cos x plus x cube plus e power x cos x. Let's find order and degree of the given differential equation. Identify the highest derivative here. D square is the highest derivative, so our order will be 2. And highest power of the highest derivative is a degree. Degree is 1. Or just write the given differential equation as d square y plus 1 into y equals to e power minus x cos x, plus cos x plus x cube plus e power x cos x. We know that d is a differential operator. Then d square will be d square by dx square. Now we can write the equation as d square y by dx square plus y equals to e power minus x plus cos x plus x cube plus e power x cos x. Here d square y by dx square is the highest derivative, so our order will be 2, and highest power of the highest derivatives are degree. Degree is 1. Right? Now coming to the problem. Given differential equation, d square plus 1 into y equals to e power minus x plus cos x plus x cube plus e power x cos x, which is in operator form. F of d into y equals to q, where f of d equals to d square plus 1 and q equals to e power minus x plus cos x plus x cube plus e power x cos x. Now we need to find the general solution to the given equation, which is given by y equals to yc plus yp. Here yc is a complementary function, yp is a particular integral. We will find yc using the roots of the auxiliary equation of the homogeneous equation of the given non-homogeneous equation. Simply by putting RHS to 0, we'll get the homogeneous equation of the given non-homogeneous equation, and we'll find yp using 1 by f of d into q. Let's find yc using the auxiliary equation. The auxiliary equation of f of d into y equals to 0 is f of m equals to 0, where f of m equals to, we have f of d square plus m, so replace differential operator with m, so that we'll get f of m equals to m square plus 1. Then our auxiliary equation becomes m square plus 1 equals to 0, then m square equals to minus 1, then m equals to plus or minus square root of minus 1, which is equals to plus or minus I. Therefore, m equals to plus or minus I are the roots of our auxiliary equation f of m equals to 0, which is a pair of purely imaginary roots, because here we don't have real part. Okay, only imaginary part we are having, so I wrote it as a pair of purely imaginary root, or we can just write it as a pair of complex conjugate roots. We know that a plus ib is a complex number, then its conjugate is a minus ib. If a minus ib is a complex number, then its conjugate will be a plus ib. So we can call a plus or minus ib as complex conjugate roots, right? If m equals to a plus or minus ib, then yc will be e power ax into cos bx, sorry, c1 cos bx plus c2 sin bx. In case of a0, we'll get e power 0 into x, which is e power 0 into c1 cos bx plus c2 sin bx, right? We know that e power 0 is 1. Then we'll get 1 into c1 cos bx plus c2 sin bx, which is c1 cos bx plus c2 sin bx. Okay. Now let's use this to write our complementary function. Compare plus or minus I with plus or minus ib. Then for b equals to 1, we'll get yc equals to c1 cos 1 into x plus c2 sin 1 into x. Then yc equals to c1 cos x plus c2 sin x. We got yc here. Therefore, yc equals to c1 cos x plus c2 sin x. Now let's find yp. We can find particular integral using 1 by f of d into q. We have f of d and q, where f of d is d square plus 1 and q is e power minus x plus cos x plus x cube plus e power x cos x is equals to 1 by f of d into first term plus 1 by f of d into second term plus 1 by d into, 1 by f of d, right? 1 by f of d into third term plus 1 by f of d into last term. Okay. The first one is of 1 by f of d into e power ax form, and second term is of 1 by f of d into cos ax form, and third term is of 1 by f of d into x power k form, and last term is of 1 by f of d into e power ax into v form. Okay, we'll find each term separately. We'll find first term 1 by d square plus 1 into e power minus x. This is of 1 by f of d into e power ax form, right? For a equals to minus 1. We have f of d equals to d square plus 1. Now let's find f of a, which is given by f of 1. Replace d with minus 1. We'll find f of minus 1. Replace d with minus 1. We'll get minus 1 whole square plus 1 equals to 1 plus 1, 2, non-zero. Since f of minus 1 is non-zero, so we can replace this d by minus 1 here. Okay, this equals to 1 by 1 plus 1 into e power minus x. This equals to 1 by 2 into e power minus x. Therefore, 1 by f of d into e power minus x equals to 1 by 2 into e power minus x. Now let's find second one. 1 by f of d into cos x. This is of 1 by f of d into cos ax form. For a equals to 1, we'll find d square, which is given by minus of a square, which is equals to minus of 1 square equals to minus 1, right? Now, let's see what happens to the denominator if we replace d square with minus 1. Always remember that the denominator must be non-zero. Okay. Now I'll take the total term. Okay, 1 by d square plus 1 into cos x. This equals to 1 by d plus d square by minus 1. Then we'll get minus 1 plus 1 into cos x, which is equals to 1 by 0 into cos x. So the denominator is 0. And we know that 1 by 0 is undefined. So total term becomes undefined if we replace d square by minus 1 here. So what we have to do? We have to write 1x into 1 by, find the derivative of f of d. Okay, if f of d is d square plus 1, then f dash of d will be 2d, right? 2d plus derivative of 1 is 0, just 2d. Right, 2d here into cos x is equals to x into, split 1 by 2d as 1 by 2 into 1 by d is equals to x into 1 by 2x by 2 into 1 by d into cos x. We know that 1 by d is an integral operator, so we can write it as integral cos x dx is equals to x by 2 into integral cos x dx is sine x. Therefore, 1 by f of d into cos x equals to 1 by 2 into x sine x. Now let's find third one. This is of 1 by f of d into x power k form. Here we are having x equals to 3. So we'll get only the first three derivatives. Cube is 3x square. Let's find d square of x cube, which is equals to derivative of x cube. We know the value of derivative of x cube, which is 3x square. Now we can write it as 3 into derivative of x square, which is equals to 3 into derivative of x square is 2x, right? This is equals to 3 2s are 6 into x. So we'll get 6x here. Now let's find d cube of x cube, which is equals to derivative of d square of x cube. We have the value of d square of x cube, which is 6x. Now we can write it as 6 into derivative of x. We know the value of derivative of x is 1, which is equals to 6, right? Next, d power 4 of x cube equals to derivative of d cube of x cube. We know the value of d cube of x cube, which is 6, and we know that derivative of a constant with respect to x is 0. So from here we'll get all derivatives of x cube 0. In general, d power k of x cube equals to 0 for k equals to 4, 5 and so on. Now coming to 3, we can write the denominator as 1 plus d square. Okay, here we have in descending order, I wrote it in ascending order. That's it. Now this is of 1 by 1 plus x form. We can write it as 1 plus x whole inverse, right? Now we can write this fraction as 1 plus d square whole inverse into x cube. Now let's expand 1 plus d square whole inverse using 1 plus x whole inverse expansion. 1 minus x plus x square minus x cube plus so on. Binomial series expansion. Now keeping all the derivatives in mind, we'll expand this. Okay, 1 plus d square whole inverse. For x equals to d square, we'll get 1 minus d square plus d square whole square minus d square whole cube plus so on. This equals to 1 minus d square plus d a power m whole power n is a power m into n. 2 2s are 4 minus d into 2 3s are 6 plus so on. We know that higher derivatives from d cube, d power 5 all are zeros, right? So we can neglect all the terms from here because from here we'll get higher derivatives from d power 4. So we can write this as expand 1 plus d square whole inverse using this. Using this formula we got 1 minus d square plus d square whole square minus d square whole cube plus so on into x cube. I'll write it more clearly. It's equals to 1 minus d square plus d square whole square minus d square whole cube plus so on into x cube. This is equals to 1 minus d square plus d power 4 minus d power 6 plus so on into x cube. Since d power k of x cube equals to 0 for k equals to 4, 5 and so on, so neglect higher derivatives from d power 4, d power 5 and so on. Okay, so we'll neglect all the terms from here, right? And this equals to 1 minus d square into x cube, which is equals to 1 into x cube is x cube minus d square of x cube. This is equals to x cube minus d square of x cube is 6x. Therefore, 1 by f of d into x cube equals to x cube minus 6x. Now find the last term. Okay, let's find the last term now. This is of 1 by f of d into e power ax into v form, right? We'll shift e power ax towards left by replacing d with d plus a, and later we'll operate v with 1 by f of d plus a. Now compare e power x with e power ax, and for a equals to 1, we'll find d plus a, which is equals to d plus 1, right? Now we'll shift e power ax towards left by replacing d with d plus 1. Is equals to e power x into 1 by expand d plus 1 whole square using a plus b whole square formula. We'll get d square plus 1 plus 2d plus 1 into cos x. Is equals to e power x into 1 by d square plus 2d plus 2 into cos x. Now, this is of 1 by some function of d into cos bx form. Okay. Now, for b equals to 1, we'll find d square, which is given by minus of b square, which is equals to minus of 1 square equals to minus 1. Now let's see what happens if we replace d square in the denominator. Okay, I'll take the denominator part. D square plus 2d plus 2, which is equals to minus 1 plus 2d plus 2, which is equals to 2d plus 2 minus 1 is plus 1, which is non-zero. Since by replacing d square by minus 1, the denominator is non-zero. What happens if we get denominator 0? We'll just get the term like this. Okay, the term becomes like this if the denominator is 0. We know that 1 by 0 is undefined, so total term becomes undefined. So always remember that the denominator must be non-zero. But luckily, in our case, the denominator is non-zero by replacing d square with minus 1. Now replace d square by minus 1, then this becomes e power x into 1 by minus 1 plus 2d plus 2 into cos x, right? This is equals to e power x into 1 by 2d plus 2 minus 1 is plus 1 into cos x. This is equals to e power x into 1 by 2d plus 1. See, in the denominator, we are having 2d plus 1. Just replace this plus with minus, then we'll get 2d minus 1. Now multiply 2d minus 1, multiply and divide 2d minus 1 to this fraction, we'll get 1 by 2d plus 1 into 2d minus 1 by 2d minus 1 into cos x is equals to e power x into 1 into 2d minus 1 is 2d minus 1 by 2d plus 1 into 2d minus 1 into cos x, which is equals to e power x into 2d minus 1 by 2d plus 1 into 2d minus 1 is a plus b into a minus b form. So we can write it as 2d whole square minus 1 square into cos x is equals to e power x into 2d minus 1 by 2d whole square is 4d square minus 1 into cos x. Again, d square appears in the denominator. So let's see what happens if we replace d square by minus 1. Always remember that the denominator must be non-zero. Okay, if I replace d square, I will get 4 into minus 1 minus 4 minus 1, which is minus 5 non-zero. So we got denominator non-zero by replacing d square by minus 1. So let's replace d square here. Okay. Then this becomes e power x into 2d minus 1 by 4 into minus 1 into cos x, which is equals to e power x into 2d minus 1 by minus 4 minus 1 into cos x, which is equals to e power x into 2d minus 1 by minus 4 minus 1 is minus 5 into cos x. Now we can split the fraction as 1 by minus 5 into 2d minus 1 into cos x. We know that 1 by minus 5 can be written as minus 1 by 5, right, into 2d cos x minus 1 into cos x is cos x. We know that d is a differential operator. Here we can write e power x into minus 1 by 5 as minus e power x by 5 into 2 into replace d by dx into cos x. Here we need to find derivative of cos x with respect to x in the next step. This becomes minus e power x by 5 into 2 into derivative of cos x with respect to x is minus sin x minus cos x. This is equals to minus e power x by 5 into minus 2 sin x minus cos x. Now take this minus inside the brackets. We'll get e power minus x by 5 into minus is plus 2 sin x. Again minus into minus plus cos x. Okay. Or we can write it as 1 by 5 into e power x into 2 sin x plus cos x. So this is the result obtained from the fourth term. Now coming to yp. Yp becomes, the result obtained from the first term is 1 by 2 into e power minus x plus result obtained from the second term is 1 by 2 into x sin x plus result obtained from the third term x cube minus 6x plus result obtained from the last term is 1 by 5 into e power x 2 sin x plus cos x. So we got yp now and we are having yc also. So let's write the general solution. The general solution is given by y equals to yc plus yp. Then y equals to yc, we have c1 cos x plus c2 sin x plus yp 1 by 2 e power minus x plus 1 by 2 x sin x plus x cube minus 6x plus 1 by 5 into e power x into 2 sin x plus cos x. This completes the problem. So we have seen a problem from higher order linear differential equations in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.